So today we're going to talk about how we could compute functions with quantum circuits. And so let's just start by looking at a little example. And so suppose we want a circuit that's going to compute the ZOR of x1 and x2. Okay. All right, so the idea that we're going to use is going to be the same regardless of which function we're computing. We're going to have multi-qubit states, and the first k qubits will be reserved for inputs, where k is the desired input length, and then we'll have another set of, say, m qubits that'll be reserved for outputs. Okay, so in this case, then we're going to need 2 qubits of the state to be reserved for the inputs x1 and x2. And then we're going to have a single qubit reserved for output, and then by the end of the calculation, that output qubit should contain the ZOR of the 2 input qubits. Okay. All right. So then and then what we would do is, okay, so we'd use 3 qubit states. Okay, so 2 qubits for the input, 1 for the output. Okay. And so then when I'm going to compute this function, I would initialize the input qubits with x1 and x2 respectively, and then the output qubit I would want to initialize, which is 0. Okay. All right, so I have then x1, x2. Tensor with 0, okay, and then the results should be x1, x2, tensor with x1 ZOR, x2. All right. However, right, if we're defining a gate to do this, right? So remember, it's got to be a unitary operator on these 3 qubit states. So it's really got to be able to take an arbitrary 3 qubit input. So really the operator that's computing this it could take an arbitrary 3 qubit input state. Okay. And so the easiest way to get the correct result here, right, would really just be take the ZOR of x1, x2, and x3, right? So that'll give me the correct output in the case where the third qubit of the input state is actually 0. Okay, so it would compute it according to this. Okay, so notice that gives the correct behavior when x3 is 0. When x3 is not 0, we don't really care what the behavior is. So moreover, you can verify that there's actually a unitary operator that affects that transformation. And then this also shows a more general principle that we'll use when we want to compute functions using quantum circuits. Okay, so more generally, so to compute this function f, so using a quantum circuit, So we'll use this transformation. Okay, so we get x1 through xk tensored with, okay, so however many zeros we need here. Okay, and then we're going to maintain those input qubits, right? So everything is nice and invertible. Okay. And we want to end up then with so F in the place of the output qubits, right? And again, really what's going on here then is if we initialize this with anything other than zeros, then we would be doing a bitwise XOR of whatever these initialized bits were with the output, but we really only care about this case, okay? And then notice really what we're saying is what the effect is on a computational basis vector here, right? So we would extend that thing linearly to a unitary transformation. Okay. And so we let then use of F, then denote the gates, computes that transformation. Extended linearly. All right, and you can also show that, so basically any function that you can compute with a classical circuit, you can compute with a quantum circuit, and you can do so with comparable efficiency. So all the sorts of number theoretic things that we've been doing in previous units on the course. So modular arithmetic, modular exponentiation, right? So things like that we'll be able to do with quantum circuits as well. Okay, so we'll just kind of take that as given in subsequent videos.